All right. There was one thing I wanted to clarify about the exam, which is that it's an entirely open resource. You can use your notes, the textbook, anything you want from the internet. The only thing I ask is that you don't talk to other people about the exam during the time that it's occurring. So I don't think I've explicitly said that, but it'll be in the instructions on the actual exam. And I'll send an announcement out tonight about all the specifics of the exam. Okay, so open note, book, and internet for all exams, including the final. But please don't consult anyone else. Okay. So I think that's the only thing I forgot to say about the exam so far. Let's open it up to questions about any of the homework problems, or we, I think, agreed that we would talk about the pair of practice exams that I sent out over the course of the last week. So if there's any questions, feel free. Let's hear what people had the most difficult time with. And if there are no questions, that's fine. We can just finish up chapter 4. I think that would be a useful, worthwhile expenditure of our time, especially since the next exam is next Thursday, and that will cover chapters 3 and 4, possibly some of 5, depending on how quickly we can move. So, any questions? Okay then, if that's the case, then let's just head straight into lecture. So, let's see here. I believe we left off, right, I told you that the set of half turns generates a group that consists of just all the half turns and translations, right? So, I think I said the union of all translations and all half turns forms a group which we denote script H, called the group generated by half turns. Okay, so here's a sketch. This essentially is just the fact that the product of any two half turns is a translation, and the product of a half turn and a translation is a translation. And the product of 3 half turns is a half turn, right? So remember we deduced that this was, this resulted in saying that an even number of half turns has product a translation and an odd number of half turns half turns is a translation followed by a half turn. Okay, so this basically just depends on this fact, and remember what it means for a set to generate a group. You just take all the elements of that set and combine them by your group law until you get back to the identity or realize that it will go forever. Okay? So that's pretty much it, right? You could say more, but we've done a lot of verifications that sets of transformations are groups. This is the facts that this fact relies on. These are the bare bones of what proves this. That's all I'm going to say. It's because I feel like, because I'll leave this empty, meaning that I didn't really give you a proof, but I have faith in you that you can verify the group axioms when you remember the definition of what it means for a set to generate a group. Okay? Okay. So far we've developed properties of translations and half terms. Namely, we came up with explicit analytic formulae for them, and then proved a bunch of facts about why they're nice transformations. Right? For example, that a half turn is a involution, right? Or that a translation has infinite order, right? These are all examples of things that we've shown. So we'll do something very similar now for reflections. Okay? So we want to get to the point where we can develop equations for reflections. Okay. So there's a acute problem in the introduction to this section in the book, and let's go over it together. Now, so let me suppose I live on a farm that's next to a river. Here's the house on the farm. Here's a line M that represents my river. And here's the barn of the farm. Okay? Here's some water. Okay, so the question is, say I want to go from the house to some point on the river, R, let's call it, and then to the barn. So I take my bucket, I take it to the river and fill it up, and I bring it to the barn. And I want to do this in the minimal distance way. Okay? How can I go, I should say, piecewise linearly? From the house to some point on the riverbank to the barn in least distance.
There should be solid-losing a system, right?
What kind of system?
Well, I mean, you have equations representing the distance between the 2 points, like between R and each point, which are functions of the distance of the location of R along the riverbank, which is the sum of the two distances.
Yeah, that's great. Great starting point, right? We have some equation for these distances, right? The distance from H to R and then R to B. Okay? So let's write that down. Okay. So that is to say, in our geometric notation, so we're looking to minimize the distance. So I heard something about calculus. So let's forget calculus for now. Suppose we don't know calculus. Okay? So we want to minimize this distance, HR plus RB. Right? So, and I guess I'll just say, now, calculus. I'm looking for some kind of synthetic response to this. Okay. So, here's what we'll do. Without writing down any equations, what we can do is imagine that the house was on the other side of the river. And then we'll have a straight line. We can define a line that passes through R and H and B. Right? So when we reflect,
Oh, the river's not a line.
the river's a line.
Oh, water piece.
Yeah, so even if the river actually was thick,
Yeah, you could.
right? You're still gonna go. Let's assume that the river ends so that you can actually be on land. But even if you weren't, you could still reflect the point and figure out the distance. Okay? But just for the purpose of not drowning this house, we'll assume that the river is not very wide. Okay? So if we reflect the house H to the other side of the river, let's call it to a point H prime, we define our point that we're looking for on the riverbank, right? To minimize this distance in the naive way, we're looking for the point R that minimizes these two distances, right? Okay, so we'll define our point R to be the intersection of lines M. So really, here's the to correct myself from accidentally putting the house in the water. So we'll call this the river bank is the line.
That's a line, yeah.
Okay. The lines M, the riverbank, and the line B, H prime. Right? So, in other words, we have our point down here, H prime, and actually, maybe use a blue marker for this. We draw our line. B, H prime, and we find that this point is the actual R we want. Okay? This first R was just a schematic. And this, my drawing is not great either, but you know.
Makes sense.
Yeah, okay. So,
A straight line is the short distance.
that's right. So the point is that in Euclidean geometry, the shortest path between 2 points is a straight line. Okay? So we somehow use the symmetry of this situation to draw a straight line between an appropriate analogous point. Okay? And our goal now is to come up with an analytic formula for such a transformation. Okay? That is to say, we're going to come up with an equation for a reflection. Okay. So, but first, so the final answer, if I were to tell you, okay, let me step back. By contrast, when we discuss the equations of translations and half-turns, I just told you what the analytic formula was, because it's somewhat easy to visualize what's going on. If I were to tell you the analytic formula for what a reflection is, it would take quite a bit of puzzling to determine how we came up with that. So first, let's define a reflection synthetically. Okay, so it's a definition. A reflection in the line M. That is to say, reflection in the line M. That is to say, a reflection depends on a line.
Like over that one?
Yeah, this is just classical terminology. I don't know why it's in instead of across, but yeah. A reflection in the line M, which is denoted sigma sub M, is a mapping defined by sigma sub M of P is just equal to P if P lies on M, right? P lies on M, and is equal to Q if P is off M and M, the line in question, is the perpendicular bisector of the line segment PQ. Okay? So, I mean, already you might guess that if we're going to write down analytic conditions to cover these two cases, it might be a little bit messy. Okay? So, just to give you an idea of what's going on here, say we have some line M and our point P, then we say sigma sub M P equal to some point Q. What that means is that this is a right angle, perpendicular.
Okay, like M kind of trivially bisects the line segment P, which means it would make sense for just to have one case, right?
Say that again.
Like, if you replace Q with the same point as P, then don't you trivially get the first answer?
Well, the line that
Next P to P.
yeah, is on M. It's a trivial, so it's not perpendicular.
Okay.
Yeah, I mean,
It could be.
so this allows us to
Yeah.
classify fixed points in a more concise way. Also, that's not technically true.
Well,
A point can't be
yeah.
perpendicular to
Right.
a line. So, is that okay? Okay. Okay, so the perpendicular part just means that that's a right angle. Okay? And the bisector says these are the same distance. Same length. Okay, that would be the bisector portion. Again, you know, my drawings are never going to be to scale or look very nice. Sorry. Okay, so before we deduce the equation of a reflection, we can say a lot of things about properties that sigma sub m possesses. Okay, so a reflection sigma sub m is an involuntary transformation that interchanges the half planes of the line M. Sigma M fixes the line L, if and only if L is equal to M, or L is perpendicular to M. Okay, so a couple of noteworthy things here. I hope that we're familiar with this notation for lines. This just means L is perpendicular to M. L is perpendicular to M. Okay, what's a half plane?
The plane?
Yeah, it's half of a plane. It has a hard edge, right? It's the standard plane just extends infinitely in every direction, but a half plane has a line that cuts it. Like Spencer said, just half of a plane. Okay? So, let's discuss the proof of this. So, first of all, sigma sub m is an involution. Since the perpendicular bisector of the line segment PQ is the same as for the line segment QP, right? Okay. Let me just add a homework exercise here. I want you to take a second and show that sigma sub m is 1 to 1 and onto, right? Because recall here in the synthetic definition, I just said it was a mapping. So technically, we should show that it is in fact bijective. Okay. So furthermore, what do we say? To continue this proof, sigma m of p is equal to p for p on m. So obviously, this implies that sigma m fixes m fixes M pointwise. Right? That is to say, it takes every point on M to itself, which is a stronger condition than any definition of fix for a set of the plane, a subset of the plane that we've had so far. Right? It's saying that legitimately every point is taken to the other one. I mean, to itself, sorry. So, in fact, M is the only line that sigma sum M fixes pointwise, right? Because if we have a perpendicular line, then we just flip around M, right? If L is perpendicular to M, then, well, for any point on L, say P, we'll take sigma sub M of P. M will always be the perpendicular bisector for this segment. Right? So you'll always end up on the same line. So sigma sub M of L is equal to L, but L is not fixed pointwise. Now, for half planes, you can break a half plane into perpendicular lines. Okay, so a half plane of M is just the union of infinitely many I should say rays perpendicular to M. Right? So that is to say, if I take, for example, the upper half plane of M, I can just express that as all the rays, obviously I can't draw them all the rays that stem from M. Okay? And all these rays lie on perpendicular lines. So we know that we just flip to the other half plane. Okay? Okay. Okay, so now yesterday Zach said he would be really upset if we didn't use mu for reflections. I have noticed I used sigma again, which was the same notation that we used for half turns, except for the fact that half turns had a point in the subscript, and now we have a line in the subscript, right? So what's going on here? Well, this is not any less frustrating, but I'll tell you the history of it anyway. So the for both half turns and reflections is from the German Spiegelung, or in English, reflection. Okay, so that is sigma sub p for a point p is sometimes thought of as a reflection about a point. We won't use that terminology, but that was common and still is in some resources instead of the term half turn. I think the author just uses that to be a little more approachable in the beginning and to draw a distinction that these are quite different in nature, right? When you have a point in the subscript versus a line in the subscript. Okay? So, now let's set out to writing the equation of an arbitrary reflection. What must this equation depend on? We're going to proceed analytically. What data do we have that defines sigma sub m? M, yeah, which we can write some equation, right? Okay, so sigma m depends on the equation of m, which, if we're working in generality, we know is just ax plus by plus c is equal to 0. Okay. So, for the moment, assume P, which we'll call, give coordinates x1, y1, is off of M. And set sigma sub m of P be equal to Q, which we'll call x2, y2. Okay. So, if this is our equation for our line M, what must the equation of a perpendicular line to M look like?
X minus AY plus, or
Sorry, say that again?
X minus AY plus.
Yeah, we'll interchange the roles of A and B, make one of them negative, whichever one we like, and then C doesn't matter, right? We don't necessarily have to carry the same C. It could be any constant. Okay? So, a line perpendicular M must have equation of the form. Okay, and how do I know that that's correct? That if I just flip A and B and make one of them negative, what result is that referring to?
You have to have a negative invariant slope.
Yeah, the negative reciprocal of a slope makes it a perpendicular line. Yeah, exactly. Let's have an equation of the form, let's see, I think, yeah, I made A negative in my notes. So, bx minus ay plus c prime is equal to 0. For any number c prime. Okay. So therefore, for P and Q, we have, because remember, the way sigma sub m is defined synthetically says that it's the perpendicular bisector of the line segment PQ. So that means it lies on some perpendicular line. Okay? So we have B x1 minus ay1 plus c prime equal to 0, and b x2 minus a y2 plus c prime is equal to 0. Okay, so if we subtract these two equations, what do we get? We get b, well, I'll write out the algebra, I guess. bx1 minus ay1 plus c prime minus bx2 minus ay2, oops, y1 plus c prime gives us bx1 minus x2 plus a times y2 minus y1 is equal to 0, right? Or put another way, we have that b x2 minus y1 is equal to a y2 minus y1. Okay? So, I'm going to label this equation star. So there are two criteria for Q being the image of P under sigma sub m, right? That is to say, the line F must be perpendicular to the line segment PQ, and it also has to bisect the line segment PQ. So here we only used that it was perpendicular to get to equation star. Now we'll use the fact that it bisects the line segment to come up with the second equation. Okay? So now we'll use the to derive a second equation. Okay, so first of all, the midpoint of PQ has a nice analytic formula, right? Is just given by the sum x1 plus x2 divided by 2, comma y1 plus y2 divided by 2, right? Okay. And just by definition, this point is on M, right? Meaning that we can plug this into the equation we have for M. Okay, so equation double star. So doing some algebra. We can arrive at this system of equations. And also a x2 plus b y2 equals negative 2c minus a x1 minus b y1. Okay, so it might not be totally transparent where we're going here, but essentially, right now, I have two linear equations in two unknowns. Remember at the beginning of this derivation, I said let P be equal to the point x1 comma x2. And then set Q, the image of P, equal to x2 comma y2. So x1 and y1 are known quantities. And we want to derive formulae for x2 and y2. There are unknowns. So what I'm saying is we have two linear equations with two unknowns. x2 and y2. So we want to solve these two equations for x2 and y2. Okay? Standard procedure, right? You just solve, say, for example, the top one for x2, and then plug that in down here, and solve for y2, and then you plug that back in up here. You get an expression for x2. Okay? So, solving for x2 and y2, yields the following. X2 is equal to x1 minus 2a times ax1 plus by1 plus c, all divided by a squared plus b squared, okay? Y2 is equal to y1 minus 2b times ax1 plus dy1 plus c, all divided by a squared plus b squared. Okay, so let me emphasize this again. X1 comma y1 was our input into sigma sub m. And x2 comma y2 are our output. Notice our formulae here involve only our inputs and the constants from the equation for m, a, b, and c. Okay? So sigma sub m of x comma y is just equal to x1 minus 2a ax1 plus b y1 plus c all over a squared plus b squared, comma y1, sorry, no ones. That was the point of rewriting. We could eliminate the subscripts now. Minus 2b times ax plus by plus c all over a squared plus b squared. This is our analytic formula for a reflection. Now, maybe you see why we went through the synthetic definition first, instead of just handing you this formula. It's not very satisfying or elucidating as to what's going on. Okay. So, now that we have a formula in hand, well, you know, actually, most of the things that we'll deduce won't even depend on that formula. But, you know, just in case you want to work analytically, this is handy. It can be useful at times. Okay. So now that we've gone through the trouble of deriving this formula and perhaps won't even use it that much, let's talk about the properties that reflections possess that make them nice transformations. Okay. So, a transformation alpha is called an isometry. If it preserves distance. That is to say, given 2 points, Q with, let's say, P prime is equal to alpha of P, and Q prime is equal to alpha of Q, we have the distance from P to Q is equal to the distance from P prime to Q prime. Okay. So this is where we begin to take a serious turn in terms of the fact that isometries are the primary tool for studying symmetry, which, if you remember the first day of class, I told you we were going to prove this result, that there are only 17 patterns that wallpaper can be on. Modulo design, but 17 ways that the geometry can be. So this is an issue of symmetry, and isometries are the transformations that allow us to study symmetry. Okay? So, in particular, a reflection sigma sub m is an isometry. Okay, and we'll actually go back over the next couple weeks and prove that some of the things that we've already discussed are also isometries. Rotations and half turns, for example. And we'll come up with, we'll do the same thing as we did for reflections today, next week for rotations. That is to say, come up with analytic expressions for the equations of a rotation. Okay? So, something here. Okay, so.
I'm gonna say it now, that doesn't mean we're all gonna have a problem.
I'm sorry?
That doesn't mean we're all gonna have a problem.
Okay, so I think we might not have another problem. Okay. So the proof is going to be broken into 4 cases and 1 with a subcase. All right, so we have 4 cases. So just for all these cases, we're going to let P and Q be distinct points. And just as in the definition of isometry, let's set P prime equal to sigma sub m of P, and Q prime equal to sigma sub m of Q. And we wish to show that the distance PQ is equal to the distance P prime Q prime. Okay, so case 1. First, we'll allow for the line determined by PQ be equal to M, or we'll allow for the line determined by P and Q to be perpendicular to M, i.e., the line determined by P and Q is some line that's fixed by sigma sub M. Okay? So, if PQ is equal to M, P prime is equal to P, and Q prime is equal to Q, and we're done. Okay? So, if PQ is perpendicular to M, well, then, of course, we have, let me draw this out. I think that's the easiest way to do this. So, let's say this is the line that's determined by P and Q, and here we have M. Remember, we're assuming that it's perpendicular, okay? And then let's operate sigma M on this. So actually I should change this a little. Let me make Q quite a bit closer. So let's say Q just happens to be closer to M, just so it's more transparent what's going on. Well, we know that sigma sub M fixes the line determined by P and Q. So Q will go somewhere on this line and P will go elsewhere on this line. Right? So this is M again. And so what we get is Q prime equal to sigma sub M of Q here. And then P prime equal to sigma sub M of P here. So that is to say, this distance is equal to this distance, right? And this distance is equal to this distance. So together, they're the same distance. Okay? So So that's kind of the trivial case, right? If the line is fixed by sigma sub M, there's not really much to show. Now, let's look at the more interesting cases. So, let's say it's 2. Now, the line determined by PQ is parallel to M. Okay? Then, again, diagrammatically, we have our line M, and we have P here, and Q here. Have a parallel line. Okay? So, by definition of sigma sub M, I get Q prime down here, and P prime down here. Okay? Then the quadrilateral formed by these 4 points is a rectangle. Right? Then the quadrilateral P, Q, Q prime, P is a rectangle. Sorry? P prime, yeah, sorry, thanks. Is a rectangle. So opposite sides must have the same length. 3, let's say one of P or Q lies on M, and the other off M. Okay, so, oh, sorry. And the line determined by PQ is not perpendicular to M. Okay, because that's already covered. We already did that case. So, okay. So without loss of generality, assume P is on M. Okay, so in case anybody hasn't seen this phrase before, what I mean is it doesn't matter which we choose to lie on M. And just so we have labels that we can use, I'll just pick P arbitrarily. Okay? So, right. Then I'll draw this diagram. So we have P, which must equal P prime since it's on M. Right? And then let's take Q. Then this must be Q prime down here. Okay. Two similar triangles, or
an isosceles.
M is the set of points that's equidistant to both Q and, for Q prime and Q, right? So that means it's equidistant to, this is how you justify that. It's, yeah, they're similar triangles, right? Yeah. We have one shared side, and yeah, I guess we already proved that these are the same. But you could also just say that since Q prime and Q are equidistant to every point on M, that these are the same, and these are the same. Okay? Since M is the set of points that are the same distance from both Q and Q prime. Right? We don't even have to appeal to triangles if we use that fact, because they're equidistant to P. Which in this case is equal to P prime. Okay? Moving right along. Now let's go to case 4, which, question? Okay, just checking. So case 4 is the case with subcases. So let's assume both P and Q are off M, and the line PQ perpendicular or parallel. Okay. Then we'll suppose well, first of all, this means that the line PQ must intersect M at some point. We'll call that R. Okay, so suppose that the line PQ intersects M at point R. So, I want to draw a picture here, and there's not enough space left on this side of the board, so I'll erase the other side.
Same argument with triangle.
Yeah, so now we're going to use a triangular argument. Yeah, good. Okay, so we have two cases now, right? Where P and Q are on the same side of M, and where they're on opposite sides. Okay, so let's draw this out. Actually, I should make that a little lower. I have more space. So in the case where they're on the same side, I have Q here, say, and P here. In fact, I should probably extend this out a little bit. Okay, and then in the other case, let's say I have P here and Q down here. So case for A and case for B. Okay, so I draw this line. Here's my intersection with M. And likewise, here's my intersection with line M here. Okay, so let's just draw our Q prime and P prime. And on this side I get Q prime here and P prime down here. Okay, so that is to say so what we know is just as in case 3, in both 4A and 4B, I have the length from RP is equal to the length of the segment RP prime. Right? Okay. So the result we want, the length PQ is equal to the length P prime Q prime, follows if we know, oh sorry, I skipped a step. We we know RP is equal to RP prime, and also RQ is equal to RQ prime, right? Same exact argument. Okay, so the result that we're after follows if we can show that R, P prime, and Q prime are collinear. Right?
It feels unnecessary for case 4A.
I'm sorry?
It feels like too much work for case 4A.
Maybe so, but
Subtract sides from triangles.
yeah. So I don't say much about triangles just because we didn't really like.
Right.
That's a little bit deeper in Euclidean geometry, so I'm trying to avoid that a little bit. But you're not wrong. That's true. Also, it's nice to be able to do one thing for both subcases. Okay. Okay. So,
Wait, so how do you justify this idea that collinearity is?
that collinearity implies that P is PQ is the same distance as P prime Q prime. So well, let's see here. Because when you add PQ together with, or rather subtract RQ from RP,
Oh, it's the same. Okay.
you get the same. And because they're equal, they're both equal, as long as they're on the same line,
Okay.
you can make that subtraction again.
Yes.
Okay?
So it is the triangle. They're just the triangles.
Yeah, it's just not explicitly referencing
Right.
the triangles. Right.
The other one's addition.
Right. Okay. So, let's let S be the midpoint of the line segment PP prime, and T the midpoint of Q prime. Add those to my diagrams here. Okay. Then we have that the line M is just the line determined by S and T. Right? Okay? And we can see, here's really where it gets kind of triangular, but I avoid saying anything. We can see that the angles, okay, and this is angle notation. I'll say this as we go. So the angle SRP For example, in this case, means we start at S, we go to R, then we go to P. That would be this angle, SR. Oh, I said P prime, right? Sorry. We start with P prime. Right, so this is the angle. Start at S, go to R, go to P prime. S, R, P prime. Is congruent i.e. same size, geometrically equivalent to the angle SRP is congruent to angle SRQ is congruent to angle SR.
Do we mean TRQ?
Yes, thank you. Right. TRQ, because that doesn't make any sense in the case where they're on the opposite side. Good, thanks. TRQ prime. Okay, so this tells us that they're all collinear, right? The fact that we have congruent angles from involving P prime all the way to Q prime means that R, P prime, and Q prime are all on the same line. R, P prime, and Q prime are collinear. Okay. So, there you have it. Good. So, in preparing for this lecture, I realized that sporadically throughout the book, they make reference to a lot of standard geometry terminology or notation, such as this angle notation, right? So here's one other thing I'll ask you to do for homework just before Tuesday, because we don't have class on Monday. I'll ask you to read section 1.2 and page 27 of the text. Okay, so I'm sorry?
Victoria Day.
Yeah, it's Victoria Day next Monday, so there's no class.
Do we have 2 holidays?
Yeah.
A week right after that.
It's Memorial Day. That's right. I know, it's insane that we're only meeting for 7 weeks and we have two holidays in that period. But
I was already for 2 Mondays off in a row.
so be it. Right, so section 1.2, I'm sorry for this, but the syllabus that I inherited glosses over that. I don't know if you're assumed to know that, but I don't think that's necessarily true. So I'll just ask you to go back and read section 1.2.
It's the same things I use in like high school geometry.
Yeah, it's the same, it's consistent with high school geometry, but I don't necessarily expect everybody to remember it. I apologize, I should have read the textbook all the way through before I started instructing. Yeah, so Ian asked, so Monday the 24th is off. Yes, that's correct. I know, mind-blowing.
Just wondering, did we solve that barn problem with the shortest lines? Did we ever get to solve that?
Yes. So, what that barn problem was What we were looking for in that barn problem was the point R on the river bank that we would have to go to fill the bucket to minimize the length that we travel.
The intersection of the H prime
And the answer was, just as Zach was saying, is if you reflect the house to the other side of the river and then draw a straight line connecting the house and the barn, it must intersect the riverbank M. And where it intersects is that point where you go from the house to the point R to the barn. So
Okay.
the upshot is by reflecting the house, we were able to draw a straight line that hit that riverbank line that we were interested in. Okay? Right, so, yeah, as I was saying, I apologize for not going over 1.2 when we were actually talking about chapter 1. But it's all definitions and terminology. There's no proofs or anything. It just tells you all about this notation, angles, and, I've been introducing it piecemeal, like, when we were talking about a quadrilateral, defined by points is just like a square symbol in front of 4 points. So hopefully, once you read that, I won't have to just be like, and this is a definition in the middle of this proof that we're
We're
doing.
just talking about the polygon first letters and saying this is a shape.
Yeah. Okay, so, yeah. So let me tell you a theorem that depends on section 2.1, a lot of the terms in section 2.1. And then you'll understand it once you'll understand it in full detail once you've read section 2.1. But
Is it 1.2 or 2.1?
I'm sorry,
1.2 or 2.1?
say that one more time.
Is it 1.2 or 2.1?
It's 1.2. It's the second section of chapter 1. It's just all the classical geometry terminology. Okay, so here's the theorem about how nice isometries are. And isometry is a collineation that preserves all the geometric properties you could ever want. Pretty much all of them. Pretty much all of them. Between this,
Like ordering?
sorry,
The ordering of points?
the quartering of things?
Ordering?
Oh, that's just to say if, what I mean by between this is if you have a line segment A, B, and C lies on that line segment,
Right.
then the image under the isometry of all those points.
So all the points are the same order. Like
Yeah.
main order reverse, which is the same order as backwards.
Yeah. So, once you read the definition of what between this means, this will be clear. And we'll talk about this tomorrow. So, yeah. I know everybody's probably studying. We'll come back to this on Tuesday. That's fine. Okay, so between this, midpoints, line segments, rays, triangles, angles. That one's kind of obvious, right? Triangles to angles. Angle measurements.
Wait,
What is an angle measurement, right?
what does an angle mean then?
Angle is
Just that it
the
exists?
angle is the geometric thing. The measurement is the number of degrees that it spans. Yeah, I know, it's ridiculous. And perpendicularity. Yeah, okay, so, again, I know this is annoying and confusing, I'm sorry.
And you already know what preserved parallelness then, right?
Yeah, because it's a collineation.
Right. So yeah.
Perpendicularity directly follow from angle measurements.
It would make sense.
Yep, that's a good assumption. So page 26 is this proof, the proof of this theorem. So read these in order. Read section 2.1 and then read the proof. I'm not going to bother to go through it now, just because I'll be using a bunch of terminology that we haven't discussed, or trying to introduce it as we go, which is not the best idea. Okay. So, let me tell you this definition.
Is this a bijective proof? Like, if it does all these things, does it automatically preserve distance? Is that how that works?
That's a good question. I think the answer is yes.
Okay.
That's a good exercise. I'm not going to say it's homework. Try to come up with a
I
counterexample.
feel like you could just scale everything smaller and it would still hold all these things.
Yeah. Yeah. I don't know the answer off the top of my head, but let's all think about that, and then we'll come back to this on Tuesday, like I said. Okay? Okay. So, definition. Part 1. Given a set of points, call it lowercase s, if the reflection sigma sub m fixes s, sigma sub m of s is just equal to s, possibly permuted around, then we say m is a line of symmetry of S. Okay? 2, the point P, capital P, is a point of symmetry of S if the half term about P fixes S. Okay? So this definition generalizes. So we already showed that a reflection is an isometry, and you might suspect that a half turn is an isometry. We haven't proven that yet. We'll get there. So what is the general definition of a symmetry of the set S? So in general, an isometry alpha such that alpha fixes S is called a symmetry of S. A symmetry is just an isometry, right? When the isometry depends on some geometric object, like a line or a point, then we sometimes use the terminology that that's a point of symmetry or a line of symmetry. But in general, a symmetry is just an isometry. Symmetry for a set is just an isometry
So
that fixes that set.
So it's like when we say symmetry is like symmetry on a triangle, like those kind of symmetry transformations.
Yeah, so if you, exactly, so we'll look at, let me give you a quick example. Okay? So let's take a regular hexagon. Okay, here's my best attempt at a regular hexagon. This is already terrible. Okay. It's great. Well, awesome, thank you. Okay, so here's a point of symmetry, right? That is to say, the half turn around P fixes this hexagon. It doesn't fix it pointwise, but it takes it to itself. The image of this hexagon under sigma sub P, so sigma sub P fixes the hexagon. P is a point of symmetry. Okay, so who can tell me a line of symmetry for an hexagon? Yeah.
The vertical into the middle.
Yeah, we could just look at this line. In fact, how many lines of symmetry does the hexagon possess? 6. 1 through the midpoint of each pair of opposite sides, and 1 through opposite angles for each pair of opposite angles. Okay, I'll just draw them out. So M1, M2, M3, M4, M5, M6. Then we have M1 through M6 are lines of symmetry for the hexagon. Now, can anybody tell me a symmetry that does not result in a line or a point of symmetry? That is to say, can anyone tell me an isometry that fixes the hexagon?
Or rotation by 60 degrees.
A rotation by 60 degrees. Yeah, a rotation by 120 degrees. Also good. Excellent. So, so let's say rho is a rotation by 60 degrees about P is a symmetry. Now, notice here, I still said about P, but that doesn't result in a point of symmetry, because a point of symmetry has to be dependent on sigma sub P, a rotation by 180 degrees. So we haven't proven that general rotations are isometries yet. But in fact, that's true.
But rho cubed.
Okay?
Yeah.
So here's an example of a symmetry that is not expressed as having a point of symmetry or a line of symmetry. Okay? Okay, so that's exactly our time. Don't forget, office hours tonight, this evening, this afternoon, 4:30 to 6, and then also tomorrow from 10 to 11:30, in case any questions arise.
The first 4 minutes of class are going to be Tier 2 as well.
Yeah, we'll go through any questions people have, and if nobody has questions, we'll continue our discussion about it. Okay? So, see you all tomorrow, and good luck in your final preparations.
Thank you.